Alright, let's continue with lesson 13, anomaly detection. We've briefly touched simple statistical methods. The z-score, you look at how far your point is from the mean. In this case, how many standard deviations are you away from the mean, and we know the mean is 0 with the z-score. And of course, you assume that your data is Gaussian distributed. Your data needs to be Gaussian distributed, which is kind of a big assumption in one way. The second series of algorithms we can use, is actually the first series of machine learning algorithms, are density-based systems, and density equals mass divided by volume. And intuitively, you can understand that if you have a lot of points clustered together, the density will be high, but the chance that it's an anomaly is very low. Now, if you have very low density, the probability if a point is an anomaly is higher. So that's the thinking behind it. So we still have our feature. We have x1 to xd features. And the probability distribution of these features, we don't know. They're drawn from a certain distribution that is not known to us. Here I've made a drawing of two of these features, x1 and x2. And the crosses here are the points, are the data. So what we're gonna do here now is we're gonna assume Gaussian for all xi. Now again, is this a big assumption or not? Well, in one way, yes, but remember that in statistics we've looked at what we call the central limit theorem. And what does the central limit theorem say? Well, if you have random variables, x1, x2, all the way to xd, are these random variables, right? If you combine them and add them all up, you will have a Gaussian. Important is to know that you will get a Gaussian no matter what the distributions of the xi's are, and that is a very powerful theorem. So that means if you have if you have a stochastic process and it is influenced by a lot of random variables, well, your outcome is going to be normal. So in one way, if you need to assume some kind of a distribution, it's better you assume Gaussian. And by the way, this is only valid if all these random variables are independent and identically distributed. You want to know more, go to the statistics refresher. Alright, so we assume these are Gaussian, and here I've written or shown the range, and here you have your first Gaussian. This is going to be mu1, and this is going to be a standard deviation sigma 1, and here you have your other Gaussian where you have a mu2 and a sigma 2. Okay, so we assume that x1 and x2 are Gaussian, so that the probability of x1 is normally distributed with a mean mu1 and a standard deviation sigma 1, and the px2, which is the probability density function. This p of x1, p of x2 is actually this one here. So your probability density function is also normal here, and it has the parameters mu2 and sigma 2. So what we're going to do now is we're gonna use MLE, maximum likelihood estimation, to estimate parameters. And the parameters are these four here. U1, U2, sigma 1, sigma 2. Okay? So basically what we're going to do, we're going to estimate these parameters using MLE as to maximize the likelihood that these parameters will result in the data that we observe. This is plain vanilla MLE, and we've done this a few times. Yeah. So I'm not gonna do all these calculations. Yeah. So you do MLE. Yeah. MLE gives you these parameters, and what you do then is, well, you make another assumption. You assume that your xi are independent. And remember if two events A and B are independent, that the probability of seeing A and B equals the probability of A times the probability of B. Yeah, so when two events are independent, the probability of A and B is just the product of the probabilities. Yeah, so that means that the probability of a point x test, yeah, equals as the product of j equals 1 to, and in this case is to 2, of the probability of xj with parameters mu j and sigma j. Yeah, that's basically our formula. So if you have d features, yeah, for d features, you have the probability of x test equals the product from j is 1 to d of p xj mu j and sigma j. Okay? Now, if the xi are not independent, or not as independent as we would like it to be, it will still rather work. Yeah, so don't worry too much about this independence condition. And now we have an anomaly, right? We have an anomaly. We have an anomaly when the probability of x test is smaller than epsilon, right? So the chance of seeing x is very low. X test is very low. Yeah. And epsilon, I mean, this is a number you choose. This could be 0.02, for example. Yeah. But if I write this here, probably if your x test is here, yeah, the chance of seeing x test for this distribution is very low. Yeah, because here it goes near 0 here. So if I draw this here, this is going to be very low and is likely to be an outlier. So this is basically how density-based systems work. And there's many variants of these.